Good morning. Let us continue with exercise 7.2. So, now today we have to take up from question number 17 onwards. So, question number 17 says, 16 is similar to it. So, I am taking up 17th. I is equal to x upon e raised power of x squared dx. Very obviously, it's a quotient of two functions out of which the denominator is a function of a function. So we take the inner function as usual, we take the inner function to be t. So what do we get? Put x squared as t so that we get 2x dx as dt. So what do we observe? That x dx is a part of dt. And so we get I is equal to dt upon 2. So dt upon 2 half I have taken outside. And here it becomes e raised power of t, which can be written as half of integral of e raised power minus t dt. Now again it's a function of a function, so we have to put minus t as, let's say, u, which gives us minus dt as du. So this gives us I is equal to half of e raised power of u. In place of dt, I'll write minus of du, which gives us minus of half e raised by u plus c. Now start substituting back. So what do we get? Half minus half of. In place of u, I will write minus t, and again in place of t, I will write x square plus c. This is the answer. Now you can clearly see that we can skip out writing the first few steps by directly assuming minus x square as t. Let's see how. So first of all, we are given I is equal to x upon e raised by x square into dt. So first, before substituting, we write it as e raised by minus x square dx. Now put this entire thing to t, and so what do we get? Minus x square as t, which gives us minus 2x dx as dt. This x dx gets absorbed in dt, and so we get I is equal to, this gives us x dx is dt upon minus 2. So you get minus half of, in place of e raised by minus x square, we'll write e raised by t. In place of x dx, we'll write dt into minus half. Minus half I've already written, so dt. And this on integrating gives us e raised by t plus c. Now substituting back in terms of x, we get e raised by minus x squared plus c, which is the same answer as obtained here. So here we have to act smartly, that we can easily skip out a few steps by substituting, thinking and substituting smartly. Okay, now same way question number 18 and 23 can be done. Like you can easily see that question number 18 is I is equal to e raised by tan inverse x dx over 1 plus x square. Clearly numerator is a function of a function. If you put the inner function tan inverse x as t, you get 1 upon 1 plus x square dx as dt. That is, the denominator gets absorbed in dt, and so directly we get e raised by t dt, which is e raised by t plus c, which is e raised power of tan inverse x plus c. Similarly, question number 23 also you put. Question number 23 is also similar, which is sine inverse x upon 1 minus x square whole under root dx. Very obviously, the derivative of sine inverse x is under root of 1 minus x square dx. So you put sine inverse x as t, and you get the needful, that is 1 upon under root of 1 minus x square dx as dt. and so the answer becomes t dt, which is t squared by 2 plus c, which on replacing back you get half of sine inverse x whole squared plus c. Now let's come to a very important question, which is question number 19. Extremely important and has to be dealt with care. That is, I is equal to e raised power 2x minus 1 upon e raised power 2x plus 1 into dx. We have to find the integral of this. Now this kind of questions you have to be always careful. See, basically first thing, when we are given an integral, we where there are more than one functions, we try to find a function whose derivative is already present here, which can be substituted and solved easily. Over here, whenever you get an exponential function in this manner, here when you find, suppose I put this as t, so its derivative is not present here. I mean, though it is present, only this part will be taken care of, this we'll still be left with. So what we do is, we will do this, that in such a case we always take e raised power x common from both numerator and denominator. Now how will this help us? Let's see. I becomes equal to e raised power x, and I said I will take it common from both numerator and denominator. So let's see. Numerator becomes e raised power x minus e raised power minus x when you have taken e raised power x common. Same way, denominator becomes e raised power x plus e raised power minus x dx. Now this gets cancelled with this. Now what we are left with? Very obviously, the numerator is the derivative of the denominator. So by doing in this manner, we have not changed the function, we have simply written it in a form which is suitable to us for integrating. You can clearly see that if you want to solve this further, you will be back to this function, because you write this as e raised power x minus 1 upon e raised power x, and this as e raised power x plus 1 upon e raised power x, and take the LCM and solve, you will be back to this function. So we have not changed the function, we have only written it in a form which is convenient for us. So now you put the denominator, which is e raised power x plus e raised power minus x as t. We get, on differentiating, e raised power x derivative is e raised power x plus e raised power minus x derivative is minus e raised power minus x. So I write it as this whole into dx is dt. So this portion gets absorbed in dt, and so I get this as dx over dt over t, which is log of mod t plus c. Now replace back, we get the answer as log of modulus of e raised power x minus e raised power minus x plus c, which is the answer. Now come to question number 20. Question number 20 is e raised power 2x minus e raised power minus 2x upon e raised power 2x plus e raised power minus 2x dx. So if we observe carefully, it is already in the form which is suitable to us. Like, the denominator is the numerator is the derivative of the denominator. So we don't have to do anything special over here. We don't have to take anything common, because it's already given in the form which is suitable. So what do? Put the denominator, that is e raised power 2x plus e raised power minus 2x as t. Now if we differentiate, what do we observe? It's not only directly the numerator. What do we get? E raised, on differentiating, it becomes 2 times e raised power of 2x minus 2 times e raised power minus 2x into dx is dt. That is, we get 2 is common, e raised power of 2x minus e raised power minus 2x dx is dt. So again this portion gets absorbed in dt, and what we get is I becomes equal to, this becomes dt upon 2, that is half of dt, and here you get t, which gives you half of log of t plus c. Just simply replace back, you get half of log of e raised power 2x minus 2x plus c, and that's the answer. Now let's come to question number 21 and 22. So first I'll take up 22, which is a direct application. I is equal to sec squared 7 minus 4x dx. We know the result for the integral of sec squared x, which is tan x. So here simply it's a function of a function. So you put 7 minus 4x as t, which gives us minus 4 dx as dt, and so I becomes equal to minus 1 upon 4 sec squared t dt, which gives us I is equal to minus 1 by 4 sec square t. The integral is directly tan t plus c, and in place of t I will write 7 minus 4x plus c, and this is the answer. Now observe 21. 21 is a similar question, but you have to write it in a form suitable to us for integration. So what is it? Tan squared 2x minus 3 into dx. This is also a function of a function, but we don't have any result for tan squared x, integral of tan squared x. But it can be converted to a form suitable for integral. That is, tan squared x can be written in terms of sec squared. So first step involved is you write it as tan squared, we know, is equal to sec squared minus 1. So I'll write it as sec squared 2x minus 3 minus 1 whole into dx. And now do the needful exactly on this on this line. So we get here I is equal to integral of sec squared 2x minus 3 dx minus integral of dx. This we will be doing by substitution, just like this. So here when you put 2x minus 3 as t, you will get the answer as exactly on this form, but here the derivative of 2x minus 3 is plus 2 dx equal to dt, and so we get the result for this as, you can try it out, it will be half of tan of 2x minus 3 minus integral of dx is x plus c, which is the answer. Now we come to, similarly we can do question number 24, 26. These are all simple straightforward applications of the method of substitution. Let's take up question number 25. This is also an important question. Now what do we get? I is equal to 1 over cos squared x 1 minus tan x whole square into dx. Now in this, again it's a product of, like in the denominator it's a product of two functions, out of which one is a function of a function. So by default we will take this as t. Let's see, but we don't see directly any derivative of this present over here. So let's see, let's start and then we will deal with it step by step. So as usual, the inner function to be treated as t. So what do we get? Put 1 minus tan x as t. On differentiating, what do we get? Minus is as it is. Derivative of tan x is sec squared x dx is equal to dt, because derivative of 1 is 0. Now this we have got. Now let's see what is given in the function. It is 1 upon cos squared x, which is nothing but sec squared x. So what do we observe? That this gets absorbed in dt, and again it's a direct application. So what do we get? This becomes, in place of this we'll be writing minus of dt upon t squared, which can be easily solved as minus of t raised to power minus 2 dt, whose integral is t raised to power minus 1 upon minus 1 plus c. This gets cancelled. I is equal to 1 upon t plus c. Replacing back, you get 1 upon 1 minus tan x plus c is the answer. Okay, now we come to the next one, that is question. Now all these remaining questions, question number 24, 26, 27, 28 are direct applications of substitution. Like you substitute the inner function of a composite function as t, and the derivative is already present. Now let's take up question number 29. I is equal to cot x log of sin x dx. Now in this case, again it's product of two functions, out of which this is function of a function. So by default we will put sin x as t. What do we get? We get cos x dx is dt. Now here we have cot x, not cos x. So we should actually write it as cos x over sin x into log of sin x into dx. So this way, this cos x dx gets absorbed in dt, and what do we get? Log of t into dt upon t. Now this again becomes a function where you have to apply the substitution again. So what do we get? Now put log t as u, which gives us 1 upon t dt as du. So this gets absorbed, and so we get I is equal to log t is u, and this is du. This gives us u squared by 2 plus c. Now start replacing back, which gives you, in place of u you will write log t whole squared plus c, and so the answer is log of, in place of t we'll write sin x whole square plus c, which is the answer. Same thing we could have done by putting this entire thing as t, because we know that integral of cot x is log sin x. So obviously derivative of log sin x would be cot x. So let's see how. Now you put log sin x as t. So what do we get? Differentiating 1 upon sin x into derivative of sin x is cos x into dx is dt, which gives us directly cot x dx is dt. So directly we see that this, if you put this as t, this is the derivative, so cot x dx becomes dt, and so we get I is equal to t dt, which is t squared by 2 plus c. Now only substituting once, we get t is what? Half of log of sin x whole squared plus c, which is the same answer as obtained here. Okay, so in the next video I'll be taking up extremely important questions from question number 30 onwards. Thank you.